Well, hey everyone, and welcome back. As promised, we will now be talking about the asthenosphere, which lies directly beneath the lithosphere. Now, just one brief note, I never mentioned the actual Greek roots of the word lithosphere, which can be helpful, just because it's not as simple of a name as the mantle or the crust. But I assumed it would be fairly obvious because of litho as in lithology and in the study of the characteristics of rocks. Lithosphere brings to mind a very rocky, and then sphere as in like biosphere or geosphere. In this case used to refer to a region, right? So the asthenosphere isn't quite as straightforward as the lithosphere for sure. But breaking it down, we've got the sphere part, which once again just refers to that region in the earth. And then the astheno comes from the Greek word for weak. And this should make sense because, as I said previously, the lithosphere is basically the uppermost rigid piece of the earth, which includes the crust and a slice of the mantle near the top of it. So the asthenosphere is when we start to get into the viscous part of the mantle. That's one important quality about the asthenosphere. It's viscous, which, much like the rest of the mantle, when we say viscous, we mean it's a flowing solid. It isn't fully liquid like the outer core. However, it is flowing, which allows for the convection currents that I talked about in the mantle video. Now, another thing about it, deformation changes here. Instead of elastically deforming with brittle failure, most of what we get down in the asthenosphere is going to be ductile deformation. Which, once again, if you're not too familiar with material science, when something deforms ductilely, it is simply that as the strain is put onto it, it doesn't fracture. It more like stretches out and deforms in a much more like the way you would expect a very viscous solid to deform. It stretches. That would be something more like folding, if you imagine it for other rocks, like a folded surface, as opposed to a faulted surface, which is the brittle failure that we see in the lithosphere. Now, in terms of thickness, the asthenosphere is generally between where the lithosphere ends, which is anywhere, averaging it a bit, anywhere between 50 and 200 kilometers of depth through anywhere between 300 and 700 kilometers, right? That's about the deepest you'll get. Obviously, this is one of the shallowest points at which the lithosphere will end, averaged a bit. Obviously, there will be some lower, particularly in the oceanic crust. But yeah, that gives you a sense of how thick the asthenosphere is. The asthenosphere does not make up all of the mantle, or the remaining part of the mantle, I should mention. If we've got a little Earth diagram, we'll say there's the crust, pretty thick crust. There's the mantle, there's our outer core, there's our inner core. If the lithosphere is this, right? That entire piece is the lithosphere. Then the asthenosphere is going to be something like that. You know, in general, it's not particularly thicker or thinner than the lithosphere. At most points, you'll find the asthenosphere to be thicker than the lithosphere, but together they make up a relatively small piece of the mantle. So that's why I left lots of open space in there. I'll just label that. There's the litho, there's the astheno, So together they make up a very small portion of the mantle. However, we differentiate the asthenosphere from the rest of the mantle because it is important to plate tectonics. Specifically, this is where the convection currents go at the very top of it, and that's where they start moving off to the side in order to have horizontal movement and move our tectonic plates. So once again, it's not like the lithosphere where it's too rigid. That's where the actual plates lie. But it's the uppermost piece of the mantle where you have the convection currents rising, and it's up to a point where it starts to cool, so the convection currents begin to sort of flatten off in their path, start going horizontally along the lithosphere, asthenosphere boundary, and then they come down into the rest of the mantle. You know, like that. And just lots of little convection currents going on within the asthenosphere. Some are going in opposite directions. That's how we get differing plate movements. You know, like convergent versus divergent boundaries. Just stuff like that. Okay. And that's mostly all I wanted to talk about. The asthenosphere is thought to be the source of basalt at mid-ocean ridges. Just a little fun fact, which does make sense, as the mid-ocean ridges, when you have magma rising, it's coming directly from the inner mantle, or what's below the lithosphere, in this case the asthenosphere. And as far as temperature goes, the asthenosphere is down to that point in the mantle where the temperature starts increasing much more quickly, and the upper boundary is usually around 1,300 degrees Celsius or so. I'll write that number down. Why not? And that's about it for the asthenosphere. It's good to know in combination with the lithosphere. Just know that these two layers together make up a piece of, they make up the entire crust and a good slice of the mantle. Not a huge portion, but a good slice. And together they are particularly important in differentiating even more specific properties, such as the solidness of the crust and upper mantle, and the pieces' roles as they pertain to plate tectonic movement. And yeah, that's about it. Hopefully this was informative, otherwise good review. Hope you guys enjoyed, and I'll see you all in the next video. Ciao.